Next up, we have the Doppler effect. You probably have heard about the word Doppler in other parts of your life, but here, very specifically, the Doppler effect applies to waves in the sense that we're talking about how the perceived frequency changes due to either the source of the observer of the wave in motion, moving. It happens for all kinds of waves, of course. It happens for water wave, and for instance, if you have the wake that a boat makes as it moves through the water, or it could have to do with light waves, which might be the red shift that you might have heard of, for us to infer that stars are moving away from us. And then also we have for sound, because we've been talking about sound so much. And in terms of sound, you're going to be changing pitches because your frequency changes. One common example is if you happen to be at like a Formula One racetrack or something, and then you're seeing this car coming at you really, really fast. As it comes towards you, you're going to hear kind of like a high-pitched whizzing, like, and then as it moves past you, suddenly drop, and this frequency would be lower, like vroom. So it's like vroom. So qualitatively, let's take a look at how this works with the help of the wonderful contributors at Wikipedia. This contributor has illustrated, first of all, a stationary source. Everything's symmetrical, nothing's moving, so you know well in full something we're very familiar with. We have a source in the middle emitting circular wavefronts. 2D. Could be spherical. And what these blue lines, they're wavefronts. They are basically the crest of the wave. So the line between, the space between two adjacent lines, between these two blue lines, will be the wavelength of the light. So right now nothing's moving, so it's symmetrical on all sides. So where you stand, you're going to hear the same sound. Now we introduce motion. The source here is moving towards the right, and because it is moving, it is catching up to its own wavefronts as it emits them. So in front of it, you see on this patch here, all the wavefronts kind of get squished and closer together because the source is catching up to them. So shorter wavelength means higher frequency. And then in the back here, the wavelength gets stretched out, higher wavelength, therefore lower frequency. Now, important to note here, the wave itself is not moving any faster. It's the same medium, so then the wave speed, the phase speed is still the same. It's the fact that the source is moving that the wavelength gets crunched up. So therefore, dividing through by the same v, you get a different frequency. But before we look at this quantitatively, let's quickly look at what happens if you move faster than the speed of sound. So this is still the case when you're moving slower than the speed of sound, but there's nothing stopping you from moving faster than the speed of sound, and that's when this happens. If you're moving so fast that you're passing your own wavefront, what you leave behind is this cone of all these different pressure adding up. You see this cone back here? That's what we call the sonic boom. It's not, sonic boom is not like one instant burst of noise as you break the sound barrier. As long as you're moving faster than the speed of sound, behind you, you're creating this big wall of pressure continuously. It just sounds like it's a single boom because this wavefront of really high pressure passes you. So you only hear it for a very short time, but it keeps moving. But you're constantly creating this high volume pressure wave behind you. Okay, moving on to the quantitative stuff. There are actually two cases to consider here. First, either the source moving or the observer moving, and the derivation is a little different. So let's consider first the source moving. So because the source is moving towards the right, we have the wavefront compressed here to the right and then stretched out in behind. To keep things simple, we're going to consider the one-dimensional case where the source and the observer, this green dot here, is along the line of the motion, so everything is nice and in 1D. If there was 2D, you take components and it still works, but we'll keep it a little simpler like that. So first off, we have to consider what is this new wavelength. So we have the observer seeing this wavefront, the leading wavefront, and then the wavefront behind it would have been back here, and that would have been the original wavelength. But because the source has moved, by the time it emits the second wavelength, that's moved forward, and so it's actually going to sit a little out here, and that's going to be our new wavelength. How long is this? Well, how long it traveled, so that's Vs, times some time, and the time is of course the period, because the period is the time between emitting two separate wavefronts. Call that T0. So lambda prime is equal to lambda naught, in this case minus Vs To. Sorry, To is just 1 over the original frequency. Lambda naught is the wave phase velocity divided by f naught. And then over here we have the the phase velocity divided by the new frequency. Rearranging, we have V over Vs, f naught equal to V over V prime, so cross multiplying, Vf is equal to V over V minus Vs, f naught. Vs, of course, is the velocity of the source, and then this is the phase speed of the wave. So this is for the case where the source is moving. Don't copy this down yet, we still have to complete the picture with the observer moving as well. Of course, this can be plus or minus depending if you're moving towards or if you're moving away, and we'll reason all that out in a second. But that's how you derive the formula for the source moving. So the second case to consider is if the observer is moving instead of the source. Because the source is staying the same, you notice all these wavefronts out here? They're all nice and symmetric, evenly spaced, and the wavefront is still separated by the original wavelength. Because nothing is, well, the source isn't moving. It's still emanating outward at a phase velocity v, but this time the observer is moving, so the observer is going to hit subsequent wavefronts sooner than otherwise. With respect to the observer then, it's seeing that the wavefront is moving towards him relative to the observer to have a new speed. The sum of v plus the v observed together. This new v is going to be the new frequency times the original wavelength, because the wavelength hasn't changed. And of course the wavelength is the original phase velocity divided by the original frequency. So we can shuffle things around and you see that the v observed, the observer velocity ends up on top, while the source ends up on the bottom. And again, this can be plus or minus depending if you're moving towards or away. And here's the relationship when the observer is moving and how the frequency changes. Quick aside, for some reason, this doesn't happen for light waves. The speed of light is the speed of light, regardless of how fast the observer is moving. So that's where all the fun of special relativity kind of spring out from. But that's for another course. here we're going to combine the two formulas that we have for Doppler. We have the new frequency is related to the old frequency, and the two observer and source part plays together the same way. Well, combines together very well. The observer goes on top, the source goes on the bottom, and these plus or minus indicates whether you're moving towards or away. Now you have to reason it out yourself. The easiest way to remember this, because the sign convention is a little different top and bottom, the easiest way to work this out is actually to think, okay, if I'm an observer and it's moving towards my source, am I going to get a higher or lower frequency? It should be higher, therefore I must use a plus on top to make it bigger. If I have a source that's moving away from me, for instance, would the frequency be higher or lower? The frequency would be lower. So I would use plus on the bottom to make the final frequency lower. And this is how you would reason out whether to use plus or minus. But there you go. That is the equation that we need for the Doppler effect. Now, for some examples.